Chalo, today we are learning how we are just going to study how the chemical potential is derived. The mathematical definition of chemical potential derived from Gibbs-Duhem equation. From Gibbs-Duhem equation, basically is summation of Ni d mu I is equal to 0. That is in general. But for pure substance, we can define G, that is the free energy, is equal to the chemical potential multiplied by the number of moles of that component. That is, if we are talking about first component, then chemical potential of first component multiplied by the number of moles of first component. From this equation 2, we can clearly define mu is equal to G upon N. The general definition of chemical potential comes from equation 3, which is free energy change per mole of that substance. From thermodynamics, we can easily define that small change in Gibbs free energy is equal to dG is equal to G naught RTlnP, where G naught is the standard free energy of that substance, R is the constant for gas constant, and G is the temperature, and P is the pressure of that substance, of that gas. Then we can write this. We can write the similar value of dG from well-known thermodynamic relations derived from Maxwell's square and Maxwell's relationship. dG is equal to vdP minus sdT. This equation at a constant temperature leads that dt becomes 0. That is, the second component becomes 0. dG is equal to vdP. Equation 6 involves dP. If you want to integrate this equation for a larger change, calculate dG, we must replace this V with P in terms of P. For that, we are using ideal gas equation Vp, PV is equal to nRT. From here, we will get V is equal to nRT upon P, put equation 7 and equation 6. That is the value of this V from equation 7. From this, we get dG is equal to nRT, dP upon P. dG is equal to nRT and dP upon V is only the rearrangement of this form equation, so that we can now go for the integration. The small change is now integrated for a larger phenomena, for a larger change. That is, this dG is integrated. Therefore, the right hand side must also be integrated. nRT is a constant. Therefore, it will come out of the integration dG. Integration of dG, nRT, dP upon P. We know that the integration of dx is x, therefore the integration of dg will be g, and nRT comes out before this integration line dq upon p. In the second line, dx upon x, integration of dx upon x is ln x, therefore we can write g is equal to nRT ln p. Plus this g naught is an integration constant which is always added in case of indefinite integrals. This G naught here, that is the integration constant, is equal to the standard free energy of that substance. Rearranging this equation, that is G naught to the changing the side of this G naught to before that we have to rearrange this equation in terms of like this: G is equal to G naught RT ln P. Now we have to change this G in the form of chemical potential. Therefore, we are dividing the whole equation by N, G upon N, G naught upon N. This N will be cancelled out. Therefore, RT ln P. G upon N in equation 3 is already defined as chemical potential. Therefore, replacing this G upon N as mu, G naught upon N as mu naught, RT ln P. Equation 10 is the mathematical definition of chemical potential. Mu is the chemical potential, mu naught is the standard chemical potential, and RT ln P. Equation 10 can again be rearranged as mu transferring to the left hand side, mu minus mu naught, or RT ln P. ln P is mu naught, mu minus mu naught upon RT, changing this side of this RT, ln P. Then now taking both the terms in power of E, that is exponential, raising this into the power of exponential, E ln P, E mu minus mu naught upon RT. This E and ln will cancel out each other, therefore giving only P from left hand side, and E की power mu minus mu RT will be on the right hand side. Equation 11 gives you the direct application of chemical potential to calculate pressure in terms of chemical potential.